Hi, everybody. So I thought I'd make these. I'm going to do problems 7, 10, and 14 on your in-class review that you did for exam 1. So that's what I'm going to do. These are the most missed questions on it. So let's get started. All right. We got the acceleration due to gravity on the moon is gm. Suppose that an astronaut on the moon has dropped an object at height h. The time it would take for the object to reach the moon's surface would be tm. The same object is dropped from the same height on Earth, where the acceleration due to gravity is ge. The time it takes to the object to reach the Earth's surface is te. Which of the following is the correct mathematical relationships of the two times? I guess I should have shown that as well. And so they give us these options: A, B, C, D, and E. What is the relationship? Let's go find out what it is. So. Here's basically the best. So I basically split this up into these are you'll see stuff like this often. So I'm going to show you one way, two ways to solve this. The first way is, so what you definitely want to do is again, this happens a lot. They'll say some situations happening on the Earth, some situations happening on the moon. How do these two quantities compare? So you see this often. I also want to mention really quickly, yeah, the moon has a different gravitational acceleration due to gravity than the Earth, and we'll figure out why that is actually later on in the year, or actually maybe even a couple of units from now. But yeah, they are different. The moon is 1/6 that of the Earth's. So we'll talk about those later. And they're all being dropped. So all these situations, so I basically have Earth. This is all Earth stuff here. This is all moon stuff over here. They're being dropped from the same height. They're being dropped from the same height. So so the displacement here, I could call it delta y, right? Delta y. And then I got displacement here. Displacement here is also delta y. They're being dropped from the same height, and they're being dropped down. So because they're being dropped down, I'm going to say this is negative h. I'll call it negative h, because h is the height at which they're both at. This is also going to be negative h here. They're also being both dropped at rest. So if they're being dropped at rest, this initial velocity is going to be 0. This initial velocity is going to be 0. So the acceleration also due to gravity, so I can draw that. So the acceleration due to gravity right there would be, so that's the acceleration vector right there. There we go. Acceleration vector, and then you got the moon's as well. So there's the moon's acceleration vector. The moon's acceleration is negative gm. Again, negative because the acceleration points down. Earth is negative ge. And so we want to find out how the times relate. So this is going to be time of the Earth. This is going to be time of the moon. All right. So what I recommend doing is you got those three kinematic equations. I'm going to use this one, that the displacement, well, I'll say here, the final position is equal to the initial position plus the initial velocity times the time plus 1/2 at squared. I'm going to subtract x naught from both sides, and that'll basically give me x final minus x initial, and that is displacement, delta x. So, but we're also dealing with, well, here, and v naught t plus 1/2 at squared. But also, though, we're dealing with vertical position, so we'll say delta y is equal to v naught t plus 1/2 at squared. Okay, so delta y for the Earth, let's plug in those values. So delta y for the Earth is negative h equals, the initial velocity for both of these is going to be 0. So 0 times t is just going to be 0. So it's going to be 0 plus 1/2. And then the acceleration on Earth is negative gm. And then time of the Earth squared. So there's that, and this can simplify to negative h equals negative gte squared over 2, and you can see the negatives cancel out, and we get that. Then you also got the moon. So with the moon, it's the same idea. So kind of using this same relationship, it's going to be, or actually kind of getting it from here. So the moon is going to be delta y of the moon is going to be v naught t, but v naught t is also 0, right? Because they're both dropped from rest. 1/2 acceleration on the moon is negative gm, parenthesize that, and then t moon squared. So this is also delta y, which it drops a height of negative h. So it's going to be negative gm tm over 2. And now so here's this relationship here. And again, negative cancels out. And I got this relationship here. And both of them are equal to h. Both are equal to h. So I'm going to set them equal to each other. Let's see what that looks like. So that'd be g of the Earth time of the Earth squared divided by 2 equals g of the moon time of the moon squared divided by 2. 2's cancel out. And all I'm left with is, who am I isolating? Am I isolating time of the Earth? Yes, I am. I'm isolating time of the Earth. So if I do that, I'll do this really quickly. It's going to be time of the Earth equals gm over ge tm squared. That's squared. Got to take the square root of both sides. So square root of this, square root of this. It's going to be te equals square root of gm over ge. And then outside of that is tm. And there you go. So that's the relationship, which is m over e, which is b. So it should give us b. Let's see if that's true. Boom, hey, yay! All right. Another way you could do this is what I call a ratio problem. So it's all the same setup. Except we're going to combine these and actually put these over each other. So it's going to be h equals g te squared over 2. And then I'm going to do that divided by h equals g tm squared over 2. And then we can see h's cancel, 2's cancel. Sorry, those g's are not the same. This is g of the Earth, this is g of the moon. And so this reduces us to 1 equals gte squared over gm tm squared. And then lastly, to isolate te, you're going to get exactly the same answer. Boom. So yeah, you can take the ratios. You can see it's a little bit faster taking the ratios, I find. But yeah. All right. So there's that one. All right. The next one is very similar to it. So this one, though, has, instead of 2 different places, there are 2 different moments in time. But we're going to solve this exactly the same way. So here I'm going to call situation A. Here I'm going to call situation B. So I've already set this up, but they basically say, in an experiment, an object is released from rest at the top of a building. Its speed v is measured as it reaches the point that is at a distance d from the point of release. So distance d. So we'll say that this is a distance d from the point of release. So distance d from the point of release. If this distance was doubled, so the distance gets doubled, what would the new speed be, assuming the air resistance is? So this is now twice d. So we've doubled the distance, and what would be the new speed? So some other things I might want to add here is that this would be my velocity, right? My velocity. My velocity at the beginning is going to be 0. So my initial velocity for A is 0, as well as here, my initial velocity for B is 0. So both of those are the same. So you can see there's things that are similar and things that are different about these. And then let's see. So we got the displacement. And again, the displacement is negative. So those arrows would be pointing down. This arrow would be pointing down here. Arrow would be pointing down. And so what I tend to do then is I also do situation A, situation B, and I make a VOVAT for each of them. And I'll say displacement delta y instead of initial and final. Just remember that if you got something like simultaneity, to split those initial and final moments up. So this is all B stuff. So, or sorry, A, B, 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 B. V naught A is 0. V naught B is also 0. V naught A. What do you think? What do you think for situation B? Do you think it's gonna be faster than situation A when it reaches the ground, or slower, or the same? Yeah, it's gonna be faster. The question is how much faster? how much faster? Is it double, triple, quadruple, a half bigger? So, okay. The acceleration is also going to be the same. The acceleration is negative g for each one, right? The acceleration for both of them points down. We're on the surface of the Earth this time. So the acceleration is going to be negative g. And so the acceleration over here is also going to be negative g. The displacement in this one is negative d. The displacement here is negative 2d. And I think that's all we really need because I got 3 bits of information, so I should be able to solve to relate the two velocities. So again, I'm going to do this 2 different ways. The first way is what I kind of consider mindless, in that I'm going to let the math do the work here. I would choose the kinematic equation that best fits this, and in my opinion, the best kinematic equation that fits this is v squared equals v naught squared plus 2a times the displacement. In this case, it'll be delta y. And then I also know for both of these situations, the initial velocity is 0. So in this general thing, I'm just going to call that 0. So my relationship here is that v equals the square root of 2a delta y. And now plugging in these two situations. In situation A, I got the relationship that velocity A is equal to the square root of 2 times negative g multiplied by the displacement, which is negative d. So this is all A stuff here. And then I can compare that with situation B. In situation B, I got VB, which is that new velocity, which is what I'm trying to compare, times the square, which equals the square root of 2 times negative g times negative 2d, and there we go. And again, I'm going to take the ratio of these two things. I'm going to take the ratio of these two things. So let's see what that looks like. So I'm going to take the ratio. I tend to do the second moment over the first. So situation B over situation A every time. I always label them A and B, and then I do situation B over situation A. So let's see what that looks like. That's going to be VB equals the square root of 2, and these negatives are going to cancel out. So it's going to be it's going to end up being 4. Sure, let's just do that. No, let's keep it. Yeah, let's make it 4. 4GD over, and then situation A is VA equals the square root of 2GD. Again, the negatives cancel out here. So, okay. And then what's nice about doing these ratio things is that stuff cancels out when you do this. That G cancels, that D cancels, and this becomes a 2. So what am I left over with? I'm left over with VB over VA equals, and then I got the square root of 2 over the square root of 1, which is just 1. So I can multiply VA to both sides, and I get VB equals a factor of the square root of 2 times VA. So VB is going to be not double, but the square root of 2 bigger than VA. And so I can go there, and that answer is B. Yay! Another way you could look at this. So again, remember that general formula, right? Remember the general formula. We started here. So once I knew like this and this, right? I knew those things. I try to find out how they're related, right? All those are related, and then I can compare this. And the formula that best fits that is alpha here. V squared equals V naught squared plus 2a times delta y. And both of them have this of 0. So now I can start to make a comparison. So this is held constant. The acceleration is held constant. So if I were to double this delta y, and that's what's happening, instead of d, it's doubling this delta y, I then can factor this out. And if I pulled this out completely, if I pulled that 2 out completely, there's still a square root under it, though. So it'd be the square root of 2 multiplied by square root of 2a delta y, which was the original velocity. This was VA basically. So VB, if this is VB, it's the square root of 2 times VA. To me, that takes a lot of intuition and is kind of harder to wrap your brain around, especially if this is your first time doing this. I would say again, this is more mathy. But what I love about it is the math just does the work for me. I don't need to think. But over time, as you start gaining an intuition on this, you would start seeing that if I doubled this with this square root under this, it's going to double by the square root of, not double, but it would increase by the square root of 2, yeah. And we'll see other things like these. I tend to call these ratio problems because of this part of it. And again, they always have the situation of they start like with this situation, then they double a variable, or they triple a variable, or quadruple, or halve a variable, or something like that. And you can see it's quite similar to problem 7 did a similar thing. It said, okay, you know, this is different from this. How do two variables compare? So they're quite similar. Let's go on to 14. All right. So 14 says the speed of a v of an automobile moving in a straight road is given in meters per second as a function of time, t, in seconds, followed by this equation. So whatever motion this automobile is doing, it's dictated by that equation right there. That's the velocity as a function of time. How far has the automobile traveled between 0 and 2 seconds? I'm going to start first by talking about, so a lot of people, if you've taken physics in the past, here's where I have to get you to unlearn stuff. The thing is that this acceleration is not constant, and kinematic equations only work, so those kinematic equations of v squared equals v naught squared plus 2ad, plus 2a times the displacement, and displacement equals v naught t plus 1/2 a t squared. V equals v naught plus a t. They only work in constant acceleration. If they don't, if it's not constant acceleration, these things fall apart, and we got to go to, we got to break out calculus. So let's see if this is constant acceleration, if you couldn't see it already. So it's the velocity is 2t cubed, right? So if I wanted to get the acceleration, that's the derivative as a function of time of the velocity function will give me the acceleration. So this derivative, this becomes 0. And then 2t cubed would become 6t squared. And you can see the acceleration is not constant as a function of time. If t equals 0, then let's do it, yeah. A of 0 is equal to 0. So the acceleration is 0. A of 1 is equal to 6 meters per second squared. A of 2 is equal to 2 squared, 4, 6, 24 meters per second squared, et cetera, et cetera, et cetera. So the acceleration is changing, and therefore the kinematic equations fall apart. They were derived upon the assumption that the acceleration is constant. So again, I'm going to rewrite this velocity function plus 2t cubed. And now, hopefully you recognize, oh, wait a minute, I remember that the displacement, or I think it's on your equation sheet too. I'll need to give you those, by the way. I'll put it on Schoology. So it's the integral from to get the displacement of something, it's the integral, the area under the graph of a velocity time graph. So from some initial time to some final time of the velocity as a function of time, dt. Okay, let's see what that looks like. So we're doing this from an integral from 0 to 2, right? Those were our limits. Yeah, 0 to 2 seconds. T equals 0 to t equals 2 seconds. So we're doing this in integral from 0 to 2, and the integral is 4 plus 2t cubed. That's the whole integral we're doing, dt. Now remember, if we do this, we can integrate both. Well, we can take this as each integral one by one. So the integral of 4 with respect to t is equal to 4t. And then the integral of 2t cubed with respect to t is, I add 1, right, to the power. So that'd be t to the 4th power. But then I got to divide then what I have here. So it's divided by 4. And then I'm evaluating this from 0 to 2. I can simplify this a little bit. This is going to be, this is t. This is going to be, my displacement is 4t plus, and this is going to be 1/2. So 2 divided by 4 is 1/2. T to the 4th power. And I'm evaluating this from 0 to 2. So now I can plug these in. I plug in each, so I plug in 2 into both of these. Then I plug in 0 into both of these. So let's see what that does. It's 4 times 2 plus 1/2 times 2 to the 4th power minus, and then plugging all this is 4 times 0 plus 1/2 times 0 to the 4th power. All this is just going to go away. I'm going to get 0. So this is all this minus 0. So I got delta x is equal to 8 plus 2 to the 4th power is 16, I think. 16. So I got 16 divided by 2, which is also 8. So 8 plus 8 is 16. So 16 meters is my displacement. Let's see if that's right. Number 14. Hey, 16 meters. All right. So there you go. Hope that helped. And all right. See you guys. Bye.